Hi guys, we're just going to give it a couple of minutes to let everyone join. We'll probably start at about 4:03. Good morning, good afternoon, and good evening, everyone. Thank you and welcome to our webinar. The webinar is Migrating Postgres Database into Kubernetes. I am Janki and I am the Marketing Manager here at StorageOS. Before handing it over to your host, Ferran Castell, I wanted to just go over some housekeeping. We anticipate the webinar to be approximately 45 minutes. Inclusive of Q&A. We will finish with a Q&A, so please make sure you put your questions into the question tab, and we will answer all of them as we can. If we don't get to all of them, then we'll come back to you individually. And lastly, we will be sharing the slides in the recording, and they'll be made available to you after. Now that that's out the way, I would like to hand it over to Ferran. Ferran.
Hey, Janki, thank you. Hello, welcome everybody. Thank you, Janki, for the introduction. So as very well Janki said, we're going to talk about Postgres today with StorageOS. My name is Ferran. StorageOS is based in London, so I'm usually based in London as well, in the United Kingdom. I have more of a background of a platform engineer, supporting 24/7 high available platforms. So just so you know. So as Janki said, we're going to do the 45 minutes. So we're going to try to skim that into both live demo and a bit of slides, so we keep track on where we are. Before we start, let me give you a bit of introduction of who we are. Most of you know who we are and use StorageOS itself, but for the ones that don't know and are a bit new also to the to the world of containerization, StorageOS is a cloud-native software-defined storage for running containerized applications in production. But what that means is that we enable stateful workloads, and we want to talk about that later, to run in a production way in Kubernetes. So to containerize stateful applications. So to start, I'm going to start giving you a bit of context on what we have, what we're going to do, and what are the challenges that we are facing. So first of all, I'm going to start with a Postgres server that happens to be in Google Cloud, in GKE. It could be in Amazon, it could be in bare metal, VMware. Everything I'm going to do today is platform agnostic, so we can do here or there. So let's have a look actually of what we have. So I'm going to move into the command line and go back and forth, so we can have a bit of a dynamic presentation of our workloads. So I'm going to go into the Postgres server. This is just a simple SSH into the Postgres, and happens to be that we have a few databases. The machine is doing nothing, it's just standard VM. This would represent your workload in your production workload, or a workload that is not containerized yet. So what we are aiming to do today in here is passing these databases into a containerized solution in Kubernetes. I'm using app 1, app 2, app 10. So you can see here the names. That essentially is an idea of every database is a service, a microservice, a part of your application, or a section even of your company or organization. So what we're going to do is move into a model where we have one big database server, or even a few clusterized, but essentially we're going to pass from what we call a pet style of database. We have to take care of it. We have to be careful. They tend to become big and expensive. No one wants really to touch them very much, into a model where we can productionize in a way that is mechanized. So we're passing into a model where we treat them as cattle. We treat them, we have to take a bit of less care of them. So we're going to send these databases that have random data injected with pgdump, with pgbench, which is just a benchmarking tool for Postgres. And we're going to send these applications in an automated fashion towards our Kubernetes cluster. So we have a Kubernetes cluster. It's a GKE cluster. Again, it could be in Amazon or wherever. We have a StorageOS installed. Today, I'm not going to really go in detail about StorageOS, but if you have any questions, just please hit the hit the questions in the chat. But StorageOS will enable us to be able to run Postgres in a safe way in Kubernetes, or persist the data that the containers run. So then we will install Postgres in Kubernetes, but instead of installing one instance, we will actually install many and send the data over to the new databases. So we're going to create one instance of Postgres for every microservice that we might have in that database. So we'll have different namespaces and different pods, different stateful sets, and one will host every database. So let's go and do it. Everything I'm going to do now is available in GitHub. So I just pushed this branch, which is a few examples. We have use cases in the repository, but essentially you can just go to GitHub and just see the YAMLs that I'm going to use actually. Cool. So first, let me give you a bit of context. I'm going to use K instead of kubectl, so don't waste your time to make things fast. Node. Cool. We have 4 nodes. StorageOS installed as a daemon set. So I already installed that. It takes 5 minutes to install tops, but more or less to give you an idea of what's running. As mentioned before, we have a daemon set, 1 pod per node, and a few other helpers. I happen to be deployed the CLI as a container as well, because I'm going to use that later. I'm going to use the StorageOS user interface or the CLI instinctively, but just so you know, guys, there is both that you can use. Cool. Now, which namespaces do we have? I created a namespace for every microservice that I want to have in my cluster. This is very synthetic, obviously, but for in your case, you could put that, let's call the data service, the authenticator service, or any other part of your application that runs in this cluster. Cool. So first of all, I'm going to start deploying Postgres. Because I have many, I want to run this as declarative. Obviously, what I'm going to do is run manually these creations, but in your case, for production, I would highly recommend to use a CI/CD environment to do everything I'm going to do now. I'm going to do it by hand so I can show you. Otherwise, the CI/CD could do it and you couldn't see it. So I'm going to create for every single namespace a stateful set, essentially with a Postgres database. And I'm going to show you actually how the stateful set looks like. Here we have it. Let's create for, so what we're doing pretty much is iterating over the microservice names. In this case, they are ordinal, so it's easy to iterate over numbers. So pretty much we're creating the same YAMLs everywhere. Now, what do we have? So if I go to app 1 and everywhere it's going to be the same, this is going to serve as an example. We have a pod, and that pod has its own persistent volume claim. This comes from the stateful set. So I'm going to show you now the YAML. So this pod matches this persistent volume claim on its data. So I'm going to show you two things. So stateful set. You might see that I'm using the crunchy data Postgres Docker image or OCI image. And you might think why I'm not using the crunchy data operator. Essentially, the operator is a way, it's a really good solution for production. It's a way to simplify a lot of the things that I'm going to show you how to do today. But I don't want too many moving pieces. I just want something that is simple enough to understand what's on the behind the scenes of persistence or state in Kubernetes. So in the end, the operator will do something very similar to this, but we'll do it for you as well. So we have a stateful set. Stateful set is a controller in Kubernetes that allows us to map persistent volume claims with pods. We have one replica, so it will enforce that we always have one container running. Very, very simple. We have a standard image for Postgres. And the important bit comes with the fact that we're mounting a volume into PG data, which is where the data of Postgres will be stored. If you want to use the write ahead log and put it in a different partition or a different volume, easily here you just add the volume for that write ahead log, and we will go to the volume claim template, which is actually the template of the definition of that persistent volume claim. Happens to be the important bit here. There are two main. The capacity, I'm just creating 10 gigs, could be 100 gigs, is under demand, and the storage class name. The storage class name is the reference to the provisioner of the storage system that goes behind the scenes. So when Kubernetes has to provision a volume, it will go and talk to StorageOS to do so. So we can see the persistent volume claim, it has mapped into the storage class, or the storage class has provisioned that persistent volume claim. We dynamically provision the persistent volumes and everything. You don't have to do anything. That's that. So now, every place or every node where StorageOS is running, it serves the user interface. So I'm going to show you that to see actually where the volumes themselves. Here. I'm using a port forward, by the way, against the cluster, so I can access the 5705 port, which is the StorageOS UI one or API, against my local host, which is connecting to the cluster itself. So we can see in the nodes that we can have the 4 nodes of the daemon set, but in the volumes, you couldn't see the volumes. That's because StorageOS maps automatically the namespaces of Kubernetes. So we are storing the data on those same nodes where we are running Kubernetes. So if we go to app 6 namespace, which is, for instance, a microservice, we can see our volume. Because the storage class specifies a replica, specifies a label, it just adds a label that says storageos.com/replicas. Now we have replicated volume. You can see here replication target 1. We could add more replicas on the fly, or do that at provisioning time, or do that per volume or per PVC. No problem. And happens to be, and that is mainly because the StorageOS influences the Kubernetes scheduler to put the pod where the volume is placed. So we have the master meaning the primary volume where the input-output operations are happening, where the Postgres is writing to. is in the same node where it's attached, meaning where the container is running. Cool. So now we have a bit of context. We know what's what. Now let's start seeing what we can do with this application. Let's start migrating data. How do we access that database that is in the same subnet? So it's obviously the network has to be accessible, but how do we match for all the resources in Kubernetes to be accessible to that external database? We do that with a external service. So that external service is a way to tell Kubernetes that there is a DNS name that has to map to one specific IP or a set of IPs, and automatically Kubernetes will manage this for us. So that IP happens to be that Postgres server where I show you that you had databases. So we will reference that service, the service pg.namespace, which the namespace is external, Postgres-external, so we will be able to access that database. So just for reference, we can see here, and actually if we can see endpoints, so we can see actually that the endpoint itself is mapping into that VM pretty much. Cool. So let's go import data. Now, how do we tell Kubernetes that there is different applications or different databases that has to go to a different instances? I did that with a simple config map. Again, I highly recommend that you do that with a CI/CD, so it's completely reproducible. These YAMLs can live in that Jenkins, in that GitOps style service, whatever you use, whatever you're happy with. So simply, and of course for production, you want this as a secret. You don't want this as a config map, and ensure that your secrets are backed by Vault or any other service that don't have the etcd information in plain text. So anyway, the important bits are the source and the destination. We will create a job that will pg dump from the source and will pg restore against the destination. Because we're using the service name I mentioned before, pg.postgres-external, that's pointing to the database from before. And then we are accessing to the namespace where the stateful set is. So we're going to create one job for each application, and each single one of them will do its own restore. If you're not very familiar with DNS names and how the DNS works in Kubernetes, don't worry too much, but you will see later on that we're just putting one application at a time. The config map. As you may notice, the config map itself had this application in the DB. But you say, hey, Ferran, how is this happening if the database itself has to change? So we're going to patch. And again, you can do these with templating or customize with K, with customize to template or generate your own templates for the config maps. So I'm just going to apply a simple patch that will go for every namespace and apply the right database name. Cool. Let's double check that I didn't make any mistakes. So we can see that the database is actually referencing the microservice name that we want to import. Cool. So now I'm going to create the jobs. And again, we're going to create one job. If you're not familiar with jobs, this is a controller that will create a pod, and it will, when it finishes, it will let it done. So it's one-off run of a specific job. Something super simple. We're just going to run a pg dump, import the database, and a pipe to a pg restore. Of course, if your database is really big and you don't want to affect, for instance, production workloads, you can put the size of the data to 1 megabyte or something on those lines, so you can ensure that there is no problems in there. Cool. So I'm going to run this and just create these jobs. Let's have a look at the pods. So we can see that for every namespace, we're creating a populate pod, which is a simple job. And actually, let's have a look at the pods. Postgres. So every single one of them has the same name in different namespaces. So we can simply access them to postgres-0.namespace, in this case, app1. Easy. Cool. So let's have a look on how are they doing. They're all completed. Let's have a look at the logs of one of them. Logs. Right. So we can simply see that it has actually imported database. It's just the PG restore output, simply and done. Now, for every single microservice, every database that we started in that microservice namespace has its own data. And we can actually have a look. And we can see in app1, we have the database app1. Very simple, we just import the data. Now, if you see that, in 5 minutes, we just have ported and migrated real-time a database into microservice architecture Kubernetes in a matter of 5 to 10 minutes with all me talking. So this is really, really easy. This is really, really simple, just using standard Kubernetes jobs, right? So let's start doing something a bit more interesting. Now, you say, okay, we move the data into Kubernetes. Is this safe? How are you handling the persistence of that Postgres when I start sending transactions of input-output operations into that application? What happens? Is this safe? Well, so as I showed you before, we have every volume. I'll show you this. I'm going to use the StorageOS CLI now instead of the user interface, just for to show you a bit of the CLI. Spaces. I made a typo. Apologies. So let me make this smaller. So we can see that we have for each namespace one volume, and that volume happens to be replicated because I specified in the storage class that I want one replica. So let me show you the storage class. StorageOS by definition creates the storage class fast, and there is then the replicated that I created. So we can see there is a label, storageos.com/replicas1, meaning I'm going to have the primary plus one more replica. So now I have an active passive model where my Postgres is running in a node. Let's have a look at the UI, which is actually easier to see, where I can have my data running on this specific node, D6XW, but look at the replica, but the replica is synchronously replicating. So the volume is sending the data synchronously to a different node. Cool, so now our data is kind of safe because if we lose that node, we can automatically fail over. There are two things that are important and we can discuss later. Is my containers have to be able to start anywhere in my cluster, and my containers have to survive failure of a node. So let's have a look at this. We can see that Postgres 0 is running in this specific node. Sorry. I'm cordoning the node, and now I'm going to delete that application, that pod itself. Why am I doing this? Well, I want to force this application to start somewhere else. Bigger. So now we can see that before it was in XV, as we can see here, and now we can see it is starting somewhere else. The container is just creating, and in a matter of seconds, we will have our data mounted and no problem starting somewhere else. Why? because StorageOS, it's running now, by the way, StorageOS gives the capability of moving my application and keeping the data underneath safe. So we can have this model where our application can start somewhere else. So now we have Postgres, and Postgres can start wherever we want. Of course, obviously, we want our application to run as close as possible to its data to have the lowest latency possible for performance reasons. And that's why the StorageOS scheduler influences the Kubernetes scheduler trying to put it close. But when I force with a cordoning of the node, or the node just fails, I force that situation, things keep running. So how do we do this? So what StorageOS is doing under the hood is, because we are presenting to the container the file system into PG data, StorageOS controls talks to the kernel of the host itself, and it registers what is called a LAN or a virtual HBA. So pretty much we are registering a standard Linux or standard POSIX device. That device is backed up by StorageOS, so StorageOS implements a full storage engine. Now, when we move that application from one place to another, the StorageOS container handles internally the path to the data, but the device itself doesn't see anything. The kernel doesn't see anything, therefore the application doesn't see anything. The file system in the Postgres application doesn't see anything. So we can move things around under the hood. Now, we can do another thing, which is a bit probably more fun, and I love doing that on live demos, which is this. We have the node in this, so let's go have a look in here. We're going to do something interesting. So cool. You see that because we moved the application, now we have the data in this node while it's attached somewhere else, right? So I'm going to take this specific node and I'm just going to shoot it. High availability means I can shoot a node, right? And a lot of people might think, are you sure you want to do that in a live demo? Yeah, this is your production system. Your production system really needs to support this. So let's make sure I'm in the right place. So xvdd. Oh, here it is. So here's the SSH into that specific node that is actually holding my data, right? I'm just going to reboot it. I'm just going to hit it and see what happens. Node is gone. The application still is running. Yeah, the application is isn't a different node, remember? Happens to be, let me redo my port forward so I can access the UI. Happened to be deleting the node, but it's upgrading my code. It's gonna work eventually. Don't worry. It just needs to hit another pod. Cool. So now we were in app 1. We have the volumes. Happens to be that the replica has been promoted. Now they're in the same nodes. The Postgres application didn't move, only the data, right? Now what StorageOS did was, I had a replica, I failed over to the replica, so now the replica has become a primary, we're safe, the data is still accessible, and I created, or StorageOS created another replica because this is declarative. I want a copy of the data. So it went to another node and just started syncing. There is not much data. There's maybe like a couple of gigs of data. It's synced fast. And the cluster is just stable. So we just literally failed over the volume and nothing has happened. Well, yeah, something has happened. We lost a node, but we have a system that self-heals. So our Postgres application in production that we just migrated is actually safe because we can use a storage system that enables that Postgres to be productionized. Let me go back. Cool. So, cool. How this happens. So, to recap a bit of what just happened, I had a Postgres that was accessing, and now it didn't do any grades, but essentially when I did the PG restore, we restored data in there. It issues grades to the primary. That primary sends in parallel to the replicas. Those receive the acknowledgement and send that to the primary, and finally it goes back to the main file system. When we lose a node, so let me do this again. When we lose the node, StorageOS promotes the replica. Now that just automatically changes the paths behind that access of the data, and it creates a new replica because this is declarative, and we said we won't have replicated. Of course, I put one replica in here, there are two, but you get the point. Our data is actually saved. We can keep doing input-output operations, no problem. Cool. So now, more or less, I finished the demo. Just shoot a note. Probably it's back already. So let me talk a bit about the. Let me talk a bit of the issues or challenges that we have to run stateful applications in Kubernetes. In this case, we have moved, in a matter of 5 to 10 minutes, a Postgres application into a cluster that actually is running an active passive model of Postgres by default for you. So no, you don't have to worry too much on all the lifting about these traditional models of active passive because it's done for you. So let me talk about stateful set or stateful applications versus stateless applications. The industry traditionally, or we have evolved as an industry to run really good stateless applications. However, stateless applications themselves are not really stateless. What we have done is decouple the state persistence to somewhere else. So they're stateless because they don't hold state where they run. So if you think about a batch processing where it processes some information or some computational workloads or even web servers, they're really good to run in parallel. They can run as many as you want. They don't hold state, or most of the applications, or they shouldn't hold state, let's put it this way. But what they're doing is delegating that state to somewhere else. What they're doing is delegating the state to stateful applications, whether it's a Postgres, an Elasticsearch, a Kafka, to object stores like S3 in Amazon, etc. So now we want to run actually those stateful applications that hold that fairly structured information in our clusters as well, because we want to take advantage of what the containers give us. However, the containers themselves start really fast, and they can provision anywhere. It's easy to distribute. It's great for that. However, those containers are ephemeral as a rule of thumb. So how do we keep them? We need a system that keep those containers or the state of those containers. Same way with nodes. Nodes are a bit less ephemeral than containers. They take a bit longer to start, whether they're VMs or they're bare metal boxes. However, we need a system that is available, is capable of supporting crashing nodes and scaling up and scaling the nodes themselves. So that's a challenge in containers. Containers are ephemeral by definition. They start, and when they stop, anything in the overlay file system is gone. Now, those containers, or there is a solution for that, which is, well, I can use the host file system themselves because the container can restart, but the host is not moving. Well, you have to be able to start the containers anywhere. The whole orchestration idea is that it doesn't matter where you're running, you should be able to start your container. Containers start really fast. What we cannot do is start moving data around. Imagine moving 100 gigs and taking the time to move 100 gigabytes over your network to start your application in a different node. You would have a failure time or a time to recovery of hours. That's just not sustainable. So we need a system that allows us to start those containers or those pods in Kubernetes in different nodes. But not only when they start, but also rescheduled and go somewhere else when that node has problems, when that node has a lot of load, etc. That cannot be traded against performance, but performance and flexibility tend to antagonize themselves. What I mean with this is we achieve the highest performance by keeping the data close to the application and do a really low latency input-output operations. However, we want the flexibility to be able to start our applications from anywhere. How do we do that without compromising on availability if I lose that node where the data is held? That we need a system that gives us that. And finally, we need a system that gives us the capacity to self-provisioning storage. And I'm going to talk a bit about this a bit later. But essentially, we need a system that you ask for storage instead of having to provision the storage yourself. So when we build a storage system that has to hold that Postgres in production, we need essentially multiple copies of data, and we need to be able to automatically fail over the paths of this data when there is a problem. Yeah, the consistency of data is fundamental here. We need to be able to start somewhere else, but with exact same data. We cannot corrupt data. We have to make sure that if the data is not in the right state, the storage system just doesn't give you the data and tells you, I'd rather not give you anything. You better solve your problem before I give you wrong data. So we need multiple copies of the data that are always synced. So synchronous replication is really important for the case being. We need to be able to access data from anywhere. I mentioned that before, but we need to be able to start containers real fast, no matter in which node they start. In a matter of seconds, or even in a minute if you want, we need that application up and running. At the same time, we don't want to trade into latency, high throughput, and predictable performance. So how do we achieve this? We achieve this by copying the data on those nodes where the application most likely is going to be running. So if we have compute nodes where we can run those containers, that storage system that serves to Postgres has to be able to keep the data close where the Postgres runs. And at the same time, if we have to go through the network, we go and we have to know how painful that's going to be. And when I say painful, I mean, how much latency can I tolerate? Am I using EBSs in Amazon? I'm going through the network. Can I live with that? I usually in there, you might have 3,000 IOPS provision, which is not much. It's expensive, but can you live with that? If the answer is yes, maybe you can live with a system that doesn't really have local volumes enforced. And finally, we need a system that is capable through API driven to talk to that system and provision the capacity that you need. You don't want a system, or let me put it in a different way. You will not go into Kubernetes and ask to provision CPUs. You will say, I want my container where there are CPUs available. Same with the storage. You will not, why do you have to provision storage and then give it to the applications? No, it's the system has to give you the capacity to provision storage. So what we're doing here is changing the model of treating databases as a service. And yes, we have to be careful and we want to have a balance, because if we go to the microservice road and everything is microservice, we can have an overhead of running a lot of the same thing. And maybe we don't want that. So for your use case, I could say, guys, get your balance right and find your balance. But why do we have to have one big instance or one big cluster that no one wants to touch, that is gigantic, that is difficult to migrate, that operations have to happen at night or during weekends, on a system where every single application has to have a generic use case, where, hey, my data microservice might be really read intensive. I want to be able to tune my Postgres database for a lot of reads, maybe with read replicas, while other parts of the application, like for instance, the authentication microservice, needs different capabilities. So let's maximize on the customization as well of the stateful application for what is meant to be. So with this model, and when we can treat databases as a service, you can really, really easy start provisioning and customizing for the needs that your workloads have. So we call that application centric, meaning the application asks for the storage and have the storage it needs. So as I showed before, we are saying that in a stateful set, I have this Postgres and I want this persistent volume claim. I didn't go and plug a new disk. I didn't go and say this disk in SDF, in /def SDF belongs to this partition in the node, and then I mount things in there. And actually, if I lose the node, I have to reorchestrate the whole thing. No. I want this data. This data belongs to this application. So we want a way to forget that we have to provision capacity. Database as a service is capable because we are running declarative and reproducible YAMLs pretty much. A lot of people love YAMLs. A lot of people hate YAMLs. But the fact is that we are using a declarative model. So when we are showing how we deploy this, the only thing we have to do is have essentially this YAML, which is 40 lines of code that or of configuration, most likely that it's going to be implemented or used by CI/CDs and template solutions. And instead of having one application, you can have hundreds just by changing this number. I put in different namespaces. So if I put this here, I will have in the same namespace. But essentially, it's really, really easy to start applications. We can take advantage of container and the container world to do the same that we did with stateless application with stateful workloads. As I mentioned before, we can do workload-specific tuning. Finally, we can do database endpoint abstraction, meaning every microservice will have its own database. We can abstract the concerns of those applications. So an application that holds, for instance, data mining process doesn't necessarily have to access the data that has users. And we can make the application just to access a database endpoint. So we are abstracting what is behind. If I have one application, one stateful set for primaries and one stateful set for read replicas, for instance, whether I scale read replicas or not, or whether I put more or bigger or smaller instances behind, is completely abstracted from the application because we're treating this from a declarative point of view. And finally, this is really, really easy to horizontally scale or easy horizontal scaling. You can see these in many ways. And I'm running out of time, so I don't want to take too much time of you. So just to finish, keep in mind that this is super easy to do. Most of you or some of you that are a bit are new to working with containers or to Kubernetes, which is most of the people, sometimes find Kubernetes really complex because there are new concepts. But essentially, just watch at what we did in 5 minutes. You do this in a reproducible way. You can start in any cluster that you start, in any cloud or any VMware or bare metal machine. You do the same that we did, and in 5 minutes, you have migrated your databases into containers in a way that actually they're very usable and sustainable to maintain. So at the same time, we can just say, I want more nodes. StorageOS runs as a daemon set. So one more node, 2 more nodes, 100 more nodes. That daemon set will start, will join the cluster. StorageOS has a distributed application or control plane, as we call it, that is aware of that. And now we can just self-provision new PVCs and new applications. Every single moving piece is already handled by the orchestrator and by the declarative model that Kubernetes enforces. So use Kubernetes architecturally makes it easy to scale, but also if you add a storage system, now you can use as many Postgres as you want, just more microservices, just add more nodes and scale. Everything is self-provisioned for you. So just to finish and give you a bit of information about how to contact us, we have a free developer edition. So StorageOS is licensed, but the free license, which is, or the developer license, is completely free. You have 5 terabytes of available capacity to use. For a lot of people, for developer clusters, even for a lot of production clusters is enough. But you can come and give us feedback, talk to us in the Slack. We are really active there, so we really appreciate feedback. Anything, you have any problems or anything you want to know, you just hit us on there and it's easy. If you want to start and install StorageOS and start playing around, again, the repository I used today is completely public. There are many use cases. but I would recommend to go to the docs first. So you can do docs.storageos.com, and in there easily you can see the installation pages. You have a self-evaluation guide that will guide you through step by step how to use it, and also how to provision volumes, benchmark a bit, play around with it. So yeah, if you have anything you want to know, just hit us on Slack or through email, anything you want to know. So now we're going to pass through questions. Probably Janky and Paul, my colleagues here, have gathered some of your questions, and we can do a bit of a Q&A. I'm a bit late, so I apologize for that. So I'll try to keep this tight.
That's cool. Thank you, Ferran. Thank you for a great presentation. We've had lots of questions come through. The first one is, why use stateful set instead of deployment?
Mm-hmm. That's actually a really good question. A deployment is designed to run stateless applications. In Kubernetes, stateless applications will be enforced, or a deployment will enforce that you have X amount of instances of that application running. But it doesn't mount necessarily volumes. The only volumes that you can use in deployments are backed by centralized storage, or what read by many volumes. And that has implications on performance and centralized file systems. But essentially, deployments will start and stop applications without taking care of the underlying file system. Stateful applications, on the other hand, have two things. One, they have ordinal names, so you can always access the same pod rather than accessing behind a load balance, level 4, but load balance access to the application. So it doesn't round robin because the DNS you are accessing to one specific place. And two, it will enforce that there is only one application running with that instance of the data. Imagine what could happen if you would have a Postgres database being accessed by 2, 3, or 4 processes against the same files. The file system would get corrupted almost immediately, or not immediately, but as soon as you start using it, things could go really bad. So stateful sets protect you from trying to mount different times the same Linux file system. It keeps you honest with one application accessing one set of data. You want more applications of that, you scale that, it will create another PVC, and instead of Postgres-0, you will have Postgres-1 with data-1, and that will always belong to that database only. Hope that explains a bit. I can go for a long time about this, but yeah.
No, great, thank you, Ferran. The next question we've got is, what are the pros and cons of StorageOS replication versus application level replication?
Yeah. I mentioned before the crunchy data operator. The crunchy data operator allows you to do just to start read replicas. It's fairly easy in general, but the thing is, we are doing here is keeping the data in active passive mode in a way that data is safe when the application fails. Read replicas are more designed for adding throughput to the reads. Yeah, you can automatically promote a replica, but that is always manual or more difficult based on a transaction log, and it adds a lot of, you have to handle all the networking or all the accessing through the new automatically promoted replicas. So in my opinion, if you need for your microservice read replicas, put the primary with active passive on StorageOS, while you put the read replicas. If the read replicas are long-lived, they are not ephemeral that you create every day, but they start and they live for a reasonable amount of time, you do the same. You put them behind StorageOS replication, and that means that you will have start times in case of failure that are almost instant. So you will start the application in a matter of seconds instead of having to re-replicate everything. So time to recovery is faster. For every application is a bit different. Stateful application is a bit different. So find the balance that you want and you need. So active passive, easy for the masters. You need throughput, add read replicas, yeah. So it's not incompatible. You have to see your balance and what do you want to achieve with that. And finally, there is a lot of orchestration that you have to do by hand that probably at 3 a.m. in the morning, getting a call you don't want to do. So you let the system that self-heal your system.
Great, thank you, Ferran. Then we've got, how can I perform backup and disaster recovery?
I didn't get the chance to show, but because I was late and I apologize for that. So you can do disaster recovery by just simply, the PG dump that I just showed is a simple job. You can use actually a cron job that, I'm not gonna do it, but I'm just gonna show it. You can run a simple job, right, in Kubernetes that runs, for instance, every night at 11 p.m. that runs a PG dump. Of course, that you want to send this either to a persistent storage volume. So if you use StorageOS volumes, you can have one pod that keeps those backups, or you can send these to safe store, to an object store. You can just pipe that, or do it a bit more sophisticated and keep it stored for a week and then recycle that information. So when you have to do a disaster recovery, the only thing you have to do is the same. The same I showed you today, the same job I showed you today, instead of, let me show you. So instead of doing a PG dump and do a PG restore from a database, you might have a backup file. And that's that. So the restore itself is not difficult. That is a full disaster recovery in the sense that you have lost all the nodes of your cluster, your data is completely gone, and there is no way to start. However, usually what ends up happening is that you lose nodes, so you can fail over, etc. But you need, obviously, a disaster recovery pipeline or procedure that is robust. And when you have a problem like this, you just have the specific YAMLs that are something like I showed, or put in the CI/CD place and say, recover, just one button, and redeploy. Everything I've done today is platform agnostic. So I could have been running these in any cluster, meaning you can have other clusters running as well. If you have you're extremely sensitive to availability and you have multi-zonal clusters and things like that, you keep those backups in a place that they're accessible through one place to another, and you can just repeat this installation in a matter of seconds. Of course, if you have 3 terabytes of data, you need to make sure that you have the capacity in the infrastructure to restore that fast enough.
Cool. Okay, I think we don't have much time, but we can take 1 or 2 more. The next one is, do you see many people doing this in production?
That's a good question. Yes, we do. StorageOS is a 4-year-old company, almost 5. We have seen the market and the industry evolve a lot. I've seen, and we see usually clusters, we see clusters of different sizes and different clients, but I've seen clusters easily with hundreds of nodes, with hundreds of databases, and they run these daily for trading, big shopping retailers. So yeah, I see these being used easily every day.
Cool. And I think we've got time for 1 more. Does StorageOS use ISCSI? Is that right? Hello?
Does StorageOS use ISCSI?
Oh yeah, I was doing that on my mind. Yeah. Sorry, I was making sure I didn't misread the words. So StorageOS uses LIO. LIO is the Linux IO library is the open source library for SCSI. That is only a library that we use to talk to the kernel and register the devices, the ones I showed before. So we use an internal protocol and self-implemented protocol to do the replication, to send data and change that. Why do we do this? The iSCSI doesn't have enough brain, let's put it this way, to control certain things. You can just put a multipath or connect things on iSCSI through the network. We needed more than this. We needed to be able to control exactly where the data is going. We do a lot of things in the client. For instance, we have a write-through cache where the data is, where the application is running. So reads in there are super fast, because if we can serve it from memory, we serve it from memory, obviously not for writes. But for instance, with iSCSI, we couldn't do these things. We would have to be reliant on the implementation. And we self-implement top to bottom the network traffic and how we handle this, the paths of data. So no, we don't use internally SCSI or the SCSI protocol.
Okay, that's it then. The other questions that we've got will respond directly to you. I'll do that after this. Thank you so much, Ferran.
Cool. Thank you everyone for attending. Yeah, if you have any questions, just hit us, and again, we're very active in Slack. Thank you very much everyone for joining today. Hope you had a productive and useful afternoon or morning or evening for some of you.
Great.
Bye.
Take care.